Can you see the screen?
Yes, sir.
All right. To an exercise. Yeah, so suppose f and g is are two continuous function, are two continuous functions on closed interval AB, which are differentiable on AB, then so that there exists a point in open interval AB such that FB minus FA times G prime C is equal to GB minus GA times F prime C. F prime C. This will be question of the assignments as well. All right, so today let's look at what. So, question: what does the first derivative determine about the behavior of the function? So which means at some point, A, how the function behaves, how it looks like, I mean, does that determined by the first derivative, or what does first derivative determine about the behavior of the function, right? So let's see. So what does it mean? So it means behavior of the function. What does that mean? So it means whether there is a maximum, whether this is function is increasing or function is decreasing, or there is a maximum or there is a minimum, or what kind of thing is it? How does it behave? So that is the question here, right? So first case is one, if f is, so assume f is continuously differentiable. Differentiable. So which means the derivative is also continuous. The derivative is also continuous on AB. Yeah, continuously differentiable. Let's say even if you can make closed interval, no problem. If this and f prime c is bigger than 0 for some c belongs to AB. Right? So this one, see, since f prime is also continuous, there exists epsilon greater than 0 such that f prime x is greater than 0 on c minus epsilon to c plus epsilon, right? Yeah? Now the claim is the following. F is increasing on c minus epsilon to c plus epsilon. Well, not going into this one, let us look at the problem in more generality, not more generality, but in this special case. So what is given? So given here f from, say, whatever you take, R to R, or yeah, given, let's say, R to R, continuously differentiable. R to R continuously differentiable, and f prime x is greater than 0 for all x. For all x in R. Alright? Then we then we will we will show that f is increasing. So how would you show? Take x1 greater than x2, 2 points in R. Fx1 by mean value theorem, there exists C belongs to x2 comma x1 such that fx1 minus fx2, x1 minus x2, f prime c. And see, this part is greater than 0. This part is greater than 0. This implies fx1 is bigger than fx2. All right. So this implies since x1 and x2 are arbitrary, f is, I mean here strictly increasing. All right, greater or equal to 0 would give you monotonically increasing. So this is actually known to you. So, so this claim is now proved. So, so the above claim, this proves actually the above claim, the above claim. So the point is, if at some point derivative is 0, it might not be increasing there, but I mean increasing at other point, but at some point, let's say C, derivative is bigger than 0, then here around C there will be a neighborhood where this will be increasing. This will be increasing. This part will be like this. So it is increasing. Right? So for example, this also happens like this here. Derivative is non-zero, so we'll get a small portion of it. So here, this part, it's increasing. This portion, it's increasing. Right? Any question here? Next is if so similarly if f prime x is less than 0 for all x in R, then f is strictly decreasing. Right, so the proof is same, just using again mean value theorem. Here it will be less than 0, so that less than 0, that will give you the decreasing property. So actually when f prime at some point C is not equal to 0, we know the behavior of the function f locally around the point C. All right. So we know whether the behavior is this is either increasing. It will be increasing if it is f prime C greater than 0. Right. So we need to assume continuously differentiable. So we need to assume continuously differentiable. So here it means this claim is increasing on this, strictly increasing, strictly increasing. And here, so in if for a continuously differentiable function f, we have this. And we know the behavior of the function locally around C. If f prime C is greater than 0, then f is strictly increasing in a neighborhood of C. If f prime C less than 0, then f is strictly decreasing in a neighborhood of C. And what if f prime C is equal to 0, then what happens? So there anything can happen. Anything can happen. For example, fx equal to x square. F prime 0 is 0. So f has minimum at x equal to 0. Again, just look at fx equal to minus x square. Here also f prime 0 is 0, and here f has a maximum at x equal to 0. Example 3, fx equal to x cube, f prime 0 is 0, but f is strictly increasing in a neighborhood 0. Right? So in this case, you see here neither increasing, in both the cases, it is neither decreasing nor increasing. Right? So in example 1, and similarly, so one can give an example in similar fashion. So example 4, fx equal to minus x cube. So f prime 0 is 0, but here f is strictly decreasing. Right? So literally anything can happen. So it can be strictly increasing, it can be strictly decreasing, or it can be neither increasing nor decreasing. It can go from, I mean, yeah, so at some point it can go to the maximum and it can be a minimum as well. So the derivative is, when derivative is 0, that gives you some interesting stuff. When derivative is 0, those things are called singularities of functions, singularities of that function. All right? So in higher dimension, this becomes much more complicated. You will not have the concept of increasing and decreasing. So things become much more complicated. But maximum minima would make sense, and this can happen again in multivariable as well. Any question here?
Yes, sir.
Yes.
So what do you mean by in three dimension we don't have the concept of increase or decrease?
Yeah. So basically, suppose it's a function from R2 to R. How do you make sense of the increasing and decreasing this? Because you don't have the ordering structure of R2, right?
Oh, okay.
You need the order structure of the domain to make sense of increasing and decreasing this. So this actually makes things a little bit easier for the functions on R to deal with, because you can look at increasing and decreasing. Increasing and decreasing has certain properties, right? It is invertible,
Hmm.
right? So
But we can still have the concept of a maxima or minima by simply looking at that we will call it a minima if all points are greater than if you go in any direction things will be greater than that.
right,
So
yeah,
we can, okay, so we
right.
can
So you
define
don't.
that.
We have the concept of maximum and minimum. There is no problem in that. We have invertibility as well. The point is this: in decreasing, strict increasing and decreasing. This part, this concept are not there. But this concept is actually makes things much more easier here in this case, because I mean, if you know it is increasing, then you know that it is invertible as well, right? It is invertible, and inverse will again be continuous. Those things will be there in R. But for those things, actually, you need to do a lot of work in higher dimension. So strictly increasing implies if strictly increasing implies if invertible. Right? So assume a function from, so f from, let's say, R to R. Well, you'll make a suitable neighborhood as well. It will work in any open set as well. All right. So how do you prove such thing? So if is strictly increasing implies f is 1 1, right? Well, here you need to assume something. This is, you need to assume on 2. This part is not there for invertibility. So it will be invertible on its range. So f is strictly increasing implies f is 1 1. So example to keep in mind is, here you look at fx equal to some ax here, in this case on 2, or you can look at fx equal to e power x as well. It is not on 2, but it is invertible on its range. So if it's 1 1, so once it is 1 1, you will get it. So once f is 1 1, set theoretic inverse exists, right? Now the question is whether the inverse is also differentiable, right? So this is interesting question. So we'll deal with that one, this one next time. Till then, you can think of this question. So in strictly increasing gives you one oneness. One oneness gives you set theoretic inverse, but whether the inverse is also differentiable and the derivative is continuous, so on. So these questions uh, one can think of. So those are very interesting question, very important question as well. So we see some behavior is most of the behavior actually is determined by the first derivative when first derivative is non-zero. When first derivative is zero, then there are a lot of possibilities which might occur here. There are a lot of possibilities, and so that becomes again an uh, interesting points where the derivative vanishes in the sense of maximum minimum. Now this to understand the behavior of the function, of course, one this is a question whether the inverse exists, and inverse is also continuous, differentiable, or continuously differentiable. These questions are this question falls as a questions on the behavior of the function. All right. So we'll come back to this question after we prove the chain rule. So the chain rule is very, very important. You might not see the full strength of the chain rule in one variable, but when you go to the multivariable, you will see the full strength of the chain rule, and it is very, very useful. So what is chain rule? So let's F from R to R, differentiable. G from R to R, again, differentiable. Functions. Define Hx is F compose G. Then H is also differentiable. Differentiable. And H prime x is F prime Gx times G prime x, which you know actually. This is nothing new to you, but I think some of you may not have seen the proof, right? Have you seen the proof of this one? Yeah, have you seen the proof of this one?
I think no, sir.
Okay. So there's a nice technique. Technique is quite, I mean, the word which we used last time as well. So here we give a proof. So you define phi x as gx uh, I mean so fix a point A in R and define like that gx minus ga by x minus a, and here g prime a. Okay, here x for if x not equal to a and here x equal to a, then phi is continuous on R. Right. We also define we also define psi x or psi y equal to fy minus fb by x minus b and here g prime b. Here x not equal to this is y. Y. For y not equal to b and here for y equal to b. Right. Then size b.
So you mean other way around? When y is equal to b, that and
Uh, here this is not g, it is f prime. Yeah, say that again. What did you say?
so it should be f prime b when y not equal to b, right?
No, it is f prime b when y equal to b. That becomes continuity. That gives you continuity, right? If you take here limit y tends to b, what do you get? F prime b.
Oh yeah, yeah. So
So that gives you continuity. So psi is also continuous on R, right? Now here you see so call this definition 1, this is 2. So here you see what you get here is, so from 1, gx minus ga is equal to x minus a times phi of x when x not equal to a, or all x not equal to a, right? Just multiply. So here x minus a, you just multiply by x minus a. So gx minus ga would be x minus a times phi of x. That's what I wrote. So call this 3. Now in 2, we incorporate the following. So here we put b equal to g of a and y equal to g of x. Right, g r to r function, so g of r lies in R only, so one can do this one in 2. Then we have here also one can just multiply f of gx minus f of ga equal to psi of gx times gx minus ga. Right? Is this fine? Here we just multiply here this y minus b, and we put b equal to g of a and y equal to g of x. Is this fine?
Yes, sir.
All right. So what is this part? This part gives you hx minus ha. Right? Right? If compose g was h here. All right. So hx minus ha is this one. Now what is this? This is equal to psi of g of x times gx minus ga. So gx minus ga, which is x minus a times phi x. X minus a times phi of x by 3. Right? Now this implies hx minus ha by x minus a is psi of gx comma phi of x. Right? Now you take limit x tends to a, hx minus ha by x minus a is equal to limit x tends to a psi of gx phi of x. Right? Psi phi both are continuous. So we have two limits, x tends to a psi of g of x minus into limit x tends to a phi of x. Now what is this? G is a continuous function. G, since G is differentiable, so G is continuous. So this gives you psi of G of A, right? And here phi is also continuous function, so this will be phi of A. Now what is, so this is G of A is B. We define in this way, so this will be f prime, that will be f prime B. So this would be psi of G of A will be f prime of G of A, and phi of A is it's nothing but G prime A, G prime A. So this limit comes there because psi and phi are continuous on R. Right? So this implies H is differentiable and H prime A, so prime GA, G prime A. Now this is true for all A in R. So this actually proves this one, right? So is the proof clear?
Yes, sir.
Okay, so the important point is defining like this. So this remember this one. This will be used a lot of places. It will keep coming back again and again. Later on, if you go into mathematics, if you don't go into mathematics, then I don't know. But yeah, in mathematics, it will come back again and again. So this is to define this kind of function. Any question here? So let me give you an exercise. This is an interesting exercise here. Oh, well, do I need to give exercise? No, maybe I should. So here, so come back here. The question whether a inverse is also differentiable, that comes from the proof of this. So maybe I should put a theorem. Suppose f is continuously differentiable and and 1 on R, then f is invertible and inverse so I should put in this form. Instead of 1 I just put this, and f prime x is greater than 0 for all x in R. Then f is invertible. Well, not equal to 0 is good enough. Invertible and inverse is also differentiable. Actually, continuously differentiable. So this is in general in R you get global inverse, but in general in higher dimension you won't get a global inverse. You will not get global inverse. That's again come back to this increasing decreasingness. That is the reason you are getting global inverse here. But locally this theorem is always true in any dimension. So this the analog of this one locally, that theorem is called inverse function theorem. So remember that theorem, this theorem. Continuously differentiable, derivative non-zero implies locally it is invertible. In this case, since we have assumed for all x not equal to in R it is not equal to 0, that gives you a global inverse. But if you assume this is not 0 at one point, you get locally around that point the inverse of it. Is this clear, the statement? Let me put another theorem. This is the global one, and this is the global one, and this is theorem local one. Suppose f from R to R. continuously differentiable. And if prime a is not equal to 0 for some a in R, then there exists epsilon greater than 0 such that f is invertible on a minus epsilon to a plus epsilon, and the inverse of f on a minus epsilon a plus epsilon is again continuously differentiable. Is this clear? So this is local in a neighborhood. At one point it is non-zero, which means in a neighborhood it will be non-zero. So on that neighborhood you will get f to invertible, and inverse is also C1. I mean this continuously differentiable, it's short form of C1. I mean short form of this one is C1. So this is a notation C1. C1 function. All right, so here in the chain rule, suppose f is not defined in whole of R, G is not defined in whole of R, then what happens? We'll come back to this proof of this theorem next time. This both of them. So here a remark I should make. In the chain rule, we do not need the functions to be defined on whole of R. What do we need? We need the range of G must contain in domain of F to make sense of F compose G. We need this one and range domain of F and G to be open sets in R. This is what we need. We need open sets to say differentiability, both sides differentiability, what I mean. And we need this to make sense of F compose G. All right. So this function, yes, yes.
So why do we need the domain to be open sets?
Well, so here, I mean, so differentiability, you should have two-sided limits, right? For differentiability, you should have two-sided limit. That is the reason.
Oh, so for h dash x to be equal to that, okay.
Yeah, so that is the reason you need, I mean, two-sided one. So that is the open set. In the boundary, you have to, if you need the derivative in one-sided limit as well, then you can make these things to work suitably, choosing properly. But in general, what you need is two-sided limit as differentiability.
Okay, sir.
All right. So in this case, we don't need this whole of R. What we need, it will work for any domain which is an open set. All right. Yeah. Any question here? So this two actually you'll see the generalization later on if you go into mathematics, and you will see much more generality, and this will become the theorem. Analogous theorem will become very, very non-trivial. But in this case, in R, we have nice increasing decreasing property of the function that will make our life easier. Okay, any question? Any question? Okay, so if there is no question, so we will see you again on Tuesday. All right. And remember this, who knows about this cropping the video, please send me an email.